PETSc is not as comprehensive as Trilinos, but it has many of the same functionalities, and so you'll get an idea of what's in Trilinos from the presentation on what's in PETSc. There's a couple of people here who are going to be available for tutoring. So what I'm going to talk about in this presentation is the following material, and I've organized it in this kind of funny way. First, I'm going to start talking about access to our DAE and ODE integrators, and then I'm going to follow that by talking about how you work with PETSc vectors and matrices. Then I'm going to talk about linear preconditioners. Then I'm going to talk about a little bit about the nonlinear solvers. And then, if time permits, I'm going to talk a little bit about how it's very important to understand performance in your code. What are the issues in performance? And it never makes sense to say, well, I have some code, it's running, I'm going to now optimize it, unless you have a lot of understanding of what the code is doing and some profiling information. So here's the organization of PETSc, and basically the organization of most algebraic solver packages, including Trilinos. At the bottom, there are the standard libraries for PETSc. That's MPI for communication, and BLAS and LAPACK for certain basic linear algebra computations, like solution with dense matrices, vector operations, and so forth. Then above that, we have something that's a profiling interface that allows you to easily gather information about where the code is spending its time during the solution process. Then above that are our basic building blocks for linear algebra, which are matrices and vectors, and what we call indices, which is a way of indexing into vectors and matrices. Then above that, we have linear solver level, which includes preconditioners and Krylov methods. I'll talk a little bit about those if you're not familiar with them. Above that is nonlinear solvers. Above that are ODE integrators. Often ODE integrators will be using nonlinear solvers. Occasionally ODE integrators just directly use linear solvers, and for explicit methods, for example, the ODE integrators actually just use the matrices and vectors here and don't use either of these pieces. Depends on the problem you're working with. And then optimization algorithms. This is Tau, which uses the linear solvers within PETSc, and also the basic building blocks of the vectors and matrices. There's another piece in PETSc that is a little difficult to understand at first, something called the DM. Now, the DM is how we in PETSc try to coordinate the interaction between what happens with your meshes and your discretizations for PDEs with the linear algebra that needs to be done to solve the PDEs. So either the linear algebra or the nonlinear algebra, or even at the ODE level. It's sort of like an adapter class that communicates information from the discretization and the mesh to the solvers to make your task of working with the solvers much simpler than you having to manage it all yourself. So before I actually talk about anything, I've got about 4 slides that are fundamentally important, even though they have nothing to do with PETSc. If you're going to do high-performance computing and program in a programming language like C or Fortran, you have to know about Valgrind and you have to use Valgrind. Because in these languages, they're not memory safe. That is, you can accidentally make mistakes where you write outside array bounds, use pointers incorrectly, and then all hell breaks loose. It's different than when you're working in a higher level package like Java, where the design is fundamentally memory safe. So Valgrind is a general debugging framework that's very useful for C and Fortran. I'm only going to talk about one thing, which is the memcheck capability. What you do is you run your program underneath Valgrind, and it'll find all the cases where you're corrupting memory, where you're accessing memory where you're not supposed to, where you're, for instance, freeing some data and then trying to reuse it later. And it presents it back to you in a very simple way. So whenever you get segmentation violations and your program crashes, you should run with Valgrind, because it'll save you endless hours of print statements and running in the debugger. And even if your code is running perfect, you should run with Valgrind to verify that it really is, because likely there's a few places where it is not.
Is it open source?
Valgrind is probably GPL. Yeah, it's GPL, but it runs on Linux and Macs. Yeah.
Does it work with C++?
Yeah, it's just a memory level thing, so it'll work with any compiled language. So, yep.
So I noticed that on the structure of PETSc, you named the second layer from the bottom to the top is a profiling set of tools. I work also developing an API and a library, and when I designed it, I thought of including a profiling layer, but then I got some criticism about the fact that there exist tools such as Valgrind for debugging, and also there are things like Algebra for profiling. So how do you justify, what is it that you include in a profiling layer of your API/library that's not given by
that's actually a very good question. Since I have unlimited time, I'll answer now. There's two parts. One is, when we started writing PETSc 20 years ago, tools like Valgrind did not exist. A lot of profiling tools were much cruder. So we were really justified in putting that in. Writing a new package today, it's more questionable. The reason we keep it is because the profiling that we do is aware of what PETSc is doing. That is aware of the different types of objects and how they interact with each other. And so these tools, so for example, Valgrind memory, it'll show you where you've mallocked everything, but it'll show you in terms of lines of code. With PETSc, with our profiling of memory, it'll show you which objects that you've created that you're thinking about. Is it a Krylov object? It is a matrix object. Of course, it's almost always a matrix object. Which particular objects are actually using the most memory? So it gives you profiling information that you can connect readily with the objects in the code. And so we consider it still of value. If it didn't do that, then I have to agree that there's great tools out there, there's probably less reason to do that. So for example, we still have code in our profiling level that checks for memory corruption, even though Valgrind does a better job. But it's there all the time. The user doesn't have to run Valgrind. For machines where Valgrind is not supported, like some of the supercomputers, it's still useful to have those things in there. Okay, so the second thing is interacting with a debugger. After you used Valgrind, sometimes you still have to use a debugger occasionally. It's really important to know the basics of using a debugger. You don't have to be an expert, but just putting in print statements is just nowhere near as effective use of your time. So when you're running in parallel, of course, this becomes tricky, because there are some parallel debuggers. Some of the larger machines have those. TotalView is a nice GUI that's a parallel debugger. But if you're working on a cluster, or you're working on your laptop but doing parallelism, it's difficult to run a debugger because you actually have several processes running at the same time. So in the PETSc level, we have a few options that are just command line options that allow you to start each of the processes in the debugger, and you can choose the debugger. And by default, we open a debugger for each MPI process inside an Xterm. So if you're running with 4 processes, you get 4 debuggers open. You can also, rather than starting in the debugger, when we detect a problem, you can have the debugger pop up. You can indicate that you want to run the debugger only on certain nodes. And all of this will work pretty much on any workstation cluster and doesn't require a parallel debugger or anything. With this, what you can do is you have something crash that's running on, say, 4 processes, but it runs fine on one. You can have it on error attach debugger, and then it'll attach the debugger to where it's crashed, and then you can go look around. Or you can start it on some number of the processes and look around as the code runs. And you're just using a standard debugger like GDB or LLDB. So here's an example. Once we've started up the program, you get this weird gibberish up here, which you kind of have to ignore. Depends on what the debugger wants to display. Now the process is in the debugger. And there may be several of them if I ran in parallel, though in this case I just ran in one. You just do continue, and the program keeps on running. And now, boom, it stopped here. And we see why it stopped. Well, I'm accessing something out of memory. I just put in a huge index there in order to get it to crash at that point. Now I found my problem really quickly. Much better than putting in print statements and so forth. Okay, I'll stop with the proselytizing now and start talking about PETSc. So the ODE DAE support in PETSc takes the following form. The user is thinking about a problem like this, where they have some function g, which is a function of time, the solution u, the derivative of the solution u, and that's equal to another function, again of time, and of the solution, which for whatever reason is put in x. Now, often this takes the simpler form here, where M is a mass matrix, and then you just have M x dot equals F. In the first case, the nonlinear problem that you'll get if you set up this, if you solve this with an implicit method, has a Jacobian that looks like this. And in the second case, the Jacobian, well, it just simplifies to be this term here. And in the simplest case, where there's no mass matrix, this is the traditional way that it's usually presented. And these are more powerful ways of doing it. So how does a user provide the information to PETSc that it needs in order to actually solve the problem? So at the highest level, the user has to provide several functions. The user provides a function f here, the function g, and then the Jacobian of the function g. This I here is for implicit. So it's the implicit function, which is this part here. And the I again is the implicit part for the function g. So the point of this is that oftentimes one will want to solve these problems depending on the structure. If it's this structure here and the problem is not stiff, one would simply use an explicit method for calculating with this. Now, an explicit method involves no solving of nonlinear equations. Basically, you just compute x at the new time step based on x at the previous time step, some combination of those terms. And so in that case, you're just providing this f function here. If you write the problem like, for example, here, and you want to solve it with a fully implicit method, that is, solving a nonlinear system at each time step to update the solution, then you would have no right-hand side function. Here what I'm doing is I'm taking this whole term and calling it g. This piece minus this is g. So you would not provide this one here, but you would provide this function and then the Jacobian. And in this case, it gets even more complex methods. Say you have ODE where part of it has stiff terms and part of it is not stiff. So this part you want to solve with an explicit method, but this part you want to solve with an implicit method. You can use the same interface to pass in the function. You pass in the f in the right-hand side function here, and then you pass in the g here and here. And in the next slide, I talk a little bit more about the details of this. Explicit methods are easy and accurate, but if they don't resolve all the timescales, you get a problem with stability, and the solution that you compute blows up. Implicit methods, on the other hand, are really robust and stable, but they require nonlinear solves. And since they require those linear or nonlinear solves, they're also tend to be much slower than explicit methods. So implicit explicit methods now are a combination of implicit methods and explicit methods. And this part here where it says they're fragile and complicated is a myth. They're actually a little fragile and a little complicated, but it's possible to put that all in the library so that you can get the benefits of explicit methods for the parts of your problem where you can use them, and the benefits of implicit where you need it. So we have a whole bunch of ODE solvers in PETSc currently. Implicit and implicit explicit RK methods, Runge-Kutta methods, which are sort of the workhorse of everything. Then there's also explicit Runge-Kutta methods, the Rose W schemes, whole families of those, different orders with different stability regions and so forth, all depending on the problem. Now, the key is the interface that you call to use any of these is exactly the same. So your PETSc code is the same, and then based on your problem and some numerical studies, you would end up selecting the particular algorithm that's best for your problem. Or if you're like me and kind of lazy, you generally just stick to the one you know is probably going to work and may not be the most efficient, but it's going to do a good job and you just use it. But if you're starting to have long run times, then you can experiment with the other ones to determine which one is optimal for your case. So there's a variety of examples in PETSc that solve sort of standard, not trivial, but not incredibly difficult problems in ODEs with our solvers and some choices for command line options. And I'll talk a bit about the details of these a little later. This, again, is things you can run later during your own time to experiment with the solvers. So let's take a little snapshot of what your code looks like when you're working with PETSc and you're solving ODEs or DAEs. Generally what happens is you have your main program up there, and you want to use our ODE solvers. So you call in to the ODE solver. The PETSc ODE solvers generally then use the PETSc nonlinear solvers, which use the PETSc linear solvers, which then use the PETSc preconditioners. All of this is transparent, and you don't have to worry about the details when you first run with it. Later, when you're optimizing for performance and trying to choose the best preconditioner, you'll want to know what's going on in the choices of the preconditioner you're using and so forth. The part that comes back to the user is, of course, the user has to provide the function evaluation that defines the DAE ODE, and optionally, depending on the algorithms, the user has to provide the Jacobian information, which is, as I presented on the previous slide, a simple function call to provide that. And then the rest of the code is just the user's code. So the PETSc programming model, this is kind of a little high-level view of where we are thinking about things, is portability is very important. We try to run on anything that's possible. So we run under Windows, we run on the largest machines, Linux, Apple. You can even run on this thing if you want to. We do this because every new machine you port to, you find something you've done wrong, and you fix it, and then you all benefit in the future. So by testing on all the different machines, we find all these corner cases where we can do something better. We really strive for high performance and scalability, that is, being able to run at scale of hundreds of thousands of cores. But at the same time, we know that most people don't have access to those machines. We know that most people are using their laptops or using a workstation or using a small cluster. And so we really care about those levels too. We don't focus really exclusively at the high end at all. The model for parallelism is distributed memory with MPI. No special compiler, you just use C or Fortran or C++. Most of the communication that takes place in the MPI program is hidden inside the PETSc objects. I know earlier in the week you learned quite a bit about MPI programming. It's very important to learn that kind of stuff. But when you use PETSc, you almost have to do none of that, because we learned how to do that a long time ago, and we embedded the communication inside our objects. So when you use our linear solvers, we're doing all the MPI underneath for you, and you don't have to worry about it at all. And the user then doesn't really program themselves the communication. Instead, they orchestrate the communication at a level of linear algebra and nonlinear solvers and so forth. And there's a couple of slides later, I think, that demonstrate how that's done. So our model is that the libraries that you interact with should be a higher level than MPI. Thus, you're not really programming MPI communication. So very briefly, don't really need this slide, but because you guys have already seen a bit about MPI, as you know, the MPI communicator specifies the set of processes where a particular thing is going to take place, particular calculation or a particular data structure. So all the PETSc objects, from vectors to nonlinear solvers to the graphics things, they all, when you construct them, they all take a communicator. And what that is simply telling the object, you're going to live in this MPI world. You're going to live on this set of processes. Often, this communicator might be MPI-COM world. It might just be, okay, I'm doing everything over the whole machine. But it doesn't have to be. You could say, okay, I'm using half my nodes to work on this subproblem and half my nodes to work on this other subproblem. The way you communicate that to PETSc is by simply passing into your constructor exactly the communicator where those objects are going to live. Certain functions in PETSc are collective. So for example, vecnorm. You have to know that when you call the norm of a vector, all the processes that share that vector have to call that at the same time, or it's all going to block, waiting for that one process that didn't call it. The actual communication takes place inside the vecnorm, but it's collective in that you have to call this on all the processes where you created this object, and no more than that, of course. Then there's lots of other operations that are not collective on objects. So vec_get_local_size, which tells you how large a piece of the vector is on that one process, doesn't require any communication. Each process can call this independent of the other processes. And we have many of these functions. In our documentations, they're all labeled as collective or not collective. And of course, collective calls must be run in the same order on all the nodes that share the object. You can't have half the nodes call vecnorm while the other call vec_dot, and then have the flip it, because the vecnorm ones are going to be waiting for all of them to call vecnorm, and the vec_dot ones are going to be waiting for them all to call the vec_dot. Okay, PETSc has an initialization. It's unfortunate. We'd like to not need it, but at the beginning of all PETSc programs is a PETSc initialize. It sets up, for example, the profiling information, error handling, other things like that. It initializes MPI unless MPI was already initialized. And you can call PETSc initialize on all the processes, or you can decide, I have this big MPI program, but I only need PETSc on half of it. So call PETSc initialize only on that half and set PETSc_COM world, the variable PETSc_COM world, to be the communicator for that half. And then PETSc will run fine on that half, just thinking it's running on the whole thing, because it doesn't know or care about the other part of the communicator. At the end of the PETSc program, you call PETSc finalize, and that's where it gathers, for example, all the logging information, reports any things about memory leaks and so forth if you've forgotten to destroy objects. It'll close down MPI if you started up MPI. This line is wrong. You can actually initialize PETSc repeatedly if you want, though we don't recommend it. You can call PETSc initialize, do something, PETSc finalize, PETSc initialize again, PETSc finalize again in a loop if you want, but there's really no reason to do that generally. So a little bit about PETSc vectors. This is how the user stores information about their solution to whatever problem they're solving. Right-hand sides for linear systems, forcing functions, and so forth. So a PETSc vector is an abstract object that represents an element of Rn, where Rn for us is, n is supposed to be pretty big, so it might be 1 billion or 2, or on your laptop it might be 1 million or so. So the PETSc vectors have all the standard vector space operations like norms, dot products, being able to scale vectors. In addition, we have ways to access directly the values on your local process with vec_get_array, and in Fortran, vec_get_array F90. There's also a lot of oddball vector operations like vec_abs, which takes the square root of the absolute value of each entry in a vector. And the reason for these oddball operations is they often appear in, like, for example, the optimization algorithms with constraints that they have to do these odd things. So by putting them in the vector class, we can optimize them, and then all the code can take advantage of that. And each person doesn't have to write their own over and over again. Then there's also things like vec_stride gather, which allows you to take subsets of vectors and put them into another vector, or take two vectors and combine them into one larger vector that contains the entries from both of those vectors. I'll talk a little bit about the assembly process, how that's done, and how one can set up arbitrary communication between different vectors with what's called a vec-scatter in PETSc. So a little bit on object-oriented design. Object-oriented design simply says that you design your software based on the operations you perform rather than the explicit representation of the data. The reason for having this kind of design, which probably you've learned about many years ago, is that it allows more freedom in the implementation. So we haven't hardwired how we store our vectors. And maybe, for some reason, for some algorithms, you want to store your vectors in a different format than for other algorithms. But the API that the user works with remains the same because the design is based on the operations you perform on the vectors, like calling an inner product, calling a norm, and so forth, not on the exact representation of the data. So PETSc vectors, as I already said, they're used for storing solutions, right-hand sides, and so forth. How do you create vectors? Well, like all PETSc objects, you create a vector by passing in a communicator, and it gives you back this abstract vector object, vec. Then you can indicate things like your size of your vector. And in this case, vec set sizes takes the local size, which is the number of terms in the vector you want to store on this process, while this is the number of terms that's going to be across the entire communicator where the vector is stored. You don't have to pass in both. If you pass in this, PETSc will split the vector up as evenly as possible. If you don't pass in this, but pass in local sizes, PETSc will figure out this for you. Now, the vec set type is really important, not so much for vectors, but for all the other objects. When you create this vector and set things like the size, it's a little different than instantiating a class in C++, because in C++, once you've instantiated that class, that defines the underlying data structure and that code that's going to be run. In PETSc, that doesn't actually happen until you call the vec set type. So PETSc objects, if you're familiar with the term, PETSc objects are all delegator objects, in that it's really an object inside the vector that stores all the vector information and the vector object operations on it. So what this means is at runtime, you can choose what representation you want to use for the vector. You don't choose it at compile time, because when you pass in this type, which is just a string name, that's the point where PETSc actually creates the internal data structure and sets up all the function pointers for working with that vector. For vectors, it's not a big deal. There's not very many different vector representations. For solvers, it's a really big deal, because for solvers, you have dozens and dozens of different solvers you want to run with. You don't want to recompile your code because you changed your Krylov method from conjugate gradient to GMRes or something else. So by having this mechanism here, you don't hardwire into the code any of these choices. They're all strings, and I'll show you in a minute, well, in the very next line, how you can access and set them from the command line. So you can set the type here with vec set type, or there's this powerful routine vec set from options. What this does is it looks in the options database, which you can think of as command line options, and from that, it makes decisions about what type of vector to use and other information about it. For vectors, as I said before, it's not a big deal, but for the Krylov solvers, it is a big deal, and for the matrices and so forth. And we'll talk more about that this time. So the whole point is that we set the types at runtime to give you the flexibility of trying many, many different types, many different algorithms, without having recompiling your code at all. Yep?
So set sizes, if you don't want to give n, means you have to give a -1 or something?
Yeah, you can pass in what's called PETSc underscore default, which is actually a -1.
Oh, okay.
Yeah. Yeah.
And you have to call that first and then only set type? Or?
There are some issues which are not perfect, and there are some limitations on the order. Ideally, we'd be able to change the types later. I don't think we still have perfect code for that. So yeah, pretty much you got to set the sizes before you set the type currently. But that's not fundamental to the design. It's just fundamental to the way we wrote the code. And we want to improve it over time. And we will improve those things over time. Parallel assembly of vectors and matrices. So a big part of what your code is doing is you're providing information that has to go into vectors, and you're providing information that has to go into the matrices. Whether you're using finite differences to compute those values, or finite element, or finite volume, or some other scheme, it doesn't really matter. You're generating numerical values, and you have to put them into the right places in the vectors. So the next few slides tell how this is done with PETSc in a parallel environment. So in PETSc, any process is free to generate any entry for a vector or a matrix. That is, even though the first process might own the first 100 entries of the vector, the first process is still free to generate a later entry into the vector, the 500th entry, which actually belongs on a different MPI process. And we have an API to make that easy for the user to do, so you don't have to write MPI code to do it yourself. So you don't have to generate entries locally. You can generate them on a different process. And we move the data during this assembly phase to get it into the location that it belongs. So let's see how this is done. There's really a three-step process. Each MPI process computes values that it wants to put into the vectors or matrices. Then once all those values have been computed, we begin a communication phase to send the values to where they actually belong. And then we complete that communication phase as a separate call. So the first step, putting values in. Each process can call vecset values as many times as it wants using the global index of the vector across the whole machine. This is the global index of the vector, sorry, the rows of the vector, setting numerical values. So this can call this any number of times. And it can either say insert the values into the vector or add them to what's already there. For finite differences, you almost always use insert values. For finite element method, you almost always use add values because you're accumulating the integrals over the processes. Once you've called this as many times as you want, you call vecassembly begin and then vecassembly end. And this part, internally, PETSc handles all the MPI communication to move the data to where it belongs. And if there's no data that has to be moved, it doesn't move any data. If there's data that has to be moved, it moves the data. So the next few slides will explain this in more detail. So here's the simplest way to set the elements of a vector. We call vecGetSize. That tells us the total size of the vector. We check our rank. And if we're rank 0, that is, if we're the very first process, we go and call vecset values for all the values. The other processes do nothing during this stage. So the first process is generating all the entries, calling vecset values. Then we call vecassembly begin, vecassembly end. So this is fine. All the values will get to where they belong in the end, because this first process will accumulate all the values, and then here it'll send them off to the process where it belongs. Yep.
Are there any circumstances where you do anything with the vector between assembly begin and assembly end?
The design for this is not that you do anything with that vector, but is you do something else with a completely unrelated object. Yeah, so I didn't really talk about that. I'll do it now, might as well. This is what some people call a split phase operation. So this sets up the communication, posts the receives, posts the sends. This waits on them. And in theory, if you have some other object, some other calculation you need to do that doesn't have anything to do with this vector, you can pop it in there, and you can get overlap of communication and computation. It's mostly a theoretical argument, to be honest. Most of the time, we just do this, because generally there's not something that can be done outside of it. We just have that flexibility. Okay, so going back to this, the drawback to this, of course, is this first processor is doing all the work of generating these entries, and then you have a massive amount of communication here as you send them out to all the other processes. So you might do this on the very first day when you're first writing your finite difference discretization. Make sure it works by doing it this way. But you're never going to do this for scalability. If you have 1,000 processes, 999 are doing nothing during this entire process, and you're sending virtually the entire vector around. So a slightly better way of doing this is, and this often is useful for finite difference methods, is you call a function called vecGetOwnershipRange. That tells you the first index that's local to this process and the last index that's local to the process. And then each process loops over its entries and generates values for those entries. And then you call vecAssembly begin and end again. Now, this is fantastic for parallelism because each process is generating exactly what belongs in that one process. And vecAssembly begin and end have to do absolutely nothing. Actually, they have to do one thing. They have to communicate and say, do you have any information you're sending to me? And they say, nope, don't have anything to send. So this is perfect parallelism. Of course, this is also unreasonable in that if you have this kind of embarrassingly parallel calculation in your code, you hardly need to use PETSc or to do anything with. So in general, what happens in real codes is you want the bulk of the entries into the vector to be set by the process that owns them, but not all of them. And so the vecAssembly then requires a small amount of communication. So let's back up and talk about, for example, the finite element method. And when you see the mesh talks later this afternoon, you'll get some more details about this. What this means is you want to partition your elements across your machine, and then each process is going to get a vector associated with entries that are associated with the elements that it owns. So when you do your numerical integration over your elements on a process, most of the entries are destined to belong to the vector that you own. Not all of them, but most of them. And that's the key to getting good performance. And at the same time, flexibility. This isn't flexible, saying everybody has to calculate exactly their own thing. The other extreme of one process calculating everything isn't good for performance. So in general, what you need is something in between. And it depends on how you handle your mesh and what your discretization is, exactly the policy for laying out the vector. So a little discussion of ghost values and how we deal with this in PETSc and most of these packages as well. So if you have meshes, either a structured mesh or an unstructured mesh, we have to partition our unknowns. So in this simple case, I'm just assuming, for example, piecewise linear finite elements where the unknowns live on the corners, and some simple finite difference scheme where the unknowns live on the mesh points. In order to do a function evaluation locally, like say a difference stencil at this point, to do a difference stencil at this point, we need values from here and here, which are local, but we'll also need values from other processes here and here. Similarly, to do the element integration for a nonlinear problem on this element, we need these two values, which are local to that element, for example, but we need this value, which is on a different element. So PETSc has this concept of what we call local vectors or ghosted vectors. A ghosted vector simply is a vector that contains local values that your process owns, plus any needed ghosted values in order to perform a particular calculation. And it may be a structured piece or an unstructured piece like this. Though PETSc has vecset values to allow putting values into a vector, PETSc also has something called vecGetArray. vecGetArray gives you direct access to the local entries as a pointer. You call vecGetArray, you have direct access, you can read and write those local values, only the local values. When you're finished, you have to call vecRestoreArray, and now you no longer have access to those local values. There's also a vecGetArray read, which gives you read access to the local values, but you can't change any values in there. And the reason for this begin and end is because the vector is really a private data structure, and you shouldn't be randomly shoving stuff in there as the code runs. This gives you a very controlled way of getting access for a limited time so that the rest of the PETSc library knows between this call and this call that you may be going in and changing those values. And only during that time can you go in and change those values. So what commonly happens for calculations on these kinds of things is you have your vector, what we call a global vector, which does not have ghost values in either of these two cases. You then construct a local vector, which is as large as this one, plus has these additional values. So it's a ghosted version of this. And PETSc has a couple of ways to communicate those. One is the vec scatter. It's the most common way. A vec scatter, you can indicate that you need these ghost values, and so it'll take from the global vector and give you local vectors that contain those extra values. Now, once you have those vectors, for example, this larger vector, you can call a vec_getArray on this vector. After you've called vec_getArray, that gives you access to all of the points, so you can do numerical integration on all of these elements using this local vector, because you've already gotten the ghost values that you need from the other process. Exactly the same situation for doing differencing over here. Here's an example of the use of vec_getArray. We just call vec_getArray, and then we loop over the local values, and we put some number in there. This is the toughest part of the presentation, this DM object. As I said before, it's an interface between the linear algebra and the meshes and the grids. Provides a connection between them. There's a few different ones that we provide by default, and you can also add your own. The DMDA, which is for Cartesian grids using finite difference methods normally. What it does is it sets up all the communication patterns as needed, for example, for the ghost points in the previous slide that I showed you. It sets up all the details of the communication pattern. It provides a way to automatically create appropriately sized vectors for these types of meshes. The DMPlex is for finite elements and finite volume methods. So it thinks about things as being organized by element. And again, it can provide local vectors and global vectors for the mesh that's laid out across the processes, and it sets up all the communication patterns that are needed for it. DM composite is a way of combining several DMs together. So if you have a part of your grid is managed as a structured grid and part is managed as an unstructured, DM composite allows you to manage the whole thing. DM network is a really cool one for handling computations that happen on graphs, like for example the power grid, or circuit boards, or a plumbing system. You can think of the simulation as running on a graph rather than on a grid. There's also a DM MOAB, and you might hear a little bit about that in later presentations, for connecting with the MOAB unstructured mesh database. So the DM object tells you information about the layout of vectors and meshes, and there's some things you can get out of a DM, which are global vectors, and all that gives you is it gives you a vector that's got the layout for the given mesh with enough room for unghosted vectors, and DM create local vector, which does the same thing except it gives you back ghosted vectors with room for the ghosted values. Then DM global to local begin and end provide a way of communicating the data from a global vector to a local vector. So this is updating ghost points for you. And again, it's organized as a begin and end to allow putting some other operation inside, though usually we don't do that. The DMDA create 2D. So this is just an example for 2D. If you want to do a structured grid finite difference, you can create your DMDA object with the following calling sequence, where you indicate what type of boundary conditions you want on the two sides, whether you have periodic, non-periodic, or then a few oddball cases like ghosted values. What type of stencil you have, whether you have a star type stencil, which is like a 5-point stencil in 2D, or a box stencil, which is a 9-point stencil. for the lowest order. Then the number of grid points of your mesh in the two directions, how many degrees of freedom you have per node, how wide your stencil is. So there's an example of a box stencil and a star stencil. And what happens is it takes the entire mesh and just divides it up in the following way, like this. And it tries to make these subregions as square as possible relative to the total mesh. So in this case, we have a 4x4 set of processes, so 16 processes. Okay, now on to PETSc matrices. In PETSc, we think of as a matrix as a linear transformation between vector spaces, so it's something you do matrix vector products with. It's never something that you would store solutions to a PDE in. It's only an operator. This is a different thing than MATLAB, where in MATLAB, a matrix can be two things. It can be an operator, or you can just think of it as a two-dimensional vector. In PETSc, matrices are only operators. So we have the same issue of forming, assembling a matrix that you have with vectors, except it's more complicated because the matrices are almost always sparse. So as with vectors, you first create a matrix with a communicator. You can set the sizes. You can set the type. You can call set from options to allow choosing the type at runtime. As I mentioned, since the matrices are almost always sparse, you can provide additional information about the sparsity pattern with these routines set pre-allocation. And these are then used by PETSc to optimize the allocation of the memory for those sparse matrices. You can set the block size, and then just like with vectors, you can call mat set values. There's also versions, mat set values local, mat set values stencil. Mat set values local allow you to put values into the matrix based on the local numbering of the unknowns on that process, including ghost points, while mat set values uses the global numbering over the entire problem. Mat set values stencil is for structured grids. It allows you to indicate the locations in the matrix via a stencil of the mesh, so the IJK coordinates in your mesh. So PETSc matrices are stored in the following way for sparse matrices. Each process gets a contiguous set of rows, and the matrix on a process is actually generally stored in two parts, what we call the diagonal part, which is this piece, and the off-diagonal part, which is all the rest. Now for PDEs, the diagonal part generally has most of the values, and this part has very few values, because this part represents the coupling in the matrix between this MPI process and all the other MPI processes. So if you've done a good partitioning of your mesh, there's not very much coupling, which means most of these values are empty, and most of the numerical values are in that part. So I'm not going to go through this in detail. It's the same as with vectors. Each process can call mat set values as many times as they want, and then mat assembly begin and end to move the values over. Same thing again as I did before. Matrices, as with all the other objects in PETSc, can have many different implementations underneath the same API. And the main things that we do with the matrix, we can set values in it, we can do a matrix multiply with it, and so forth. But underneath, there's a lot of different ways we store the matrix depending on the problem that you're doing. What we call AIJ, which is compressed sparse row, or a block version of that, or symmetric storage, or dense storage. Sometimes even the matrix is matrix-free, where you don't actually ever put values into the matrix, but it's defined, for example, by differencing on a function. There's more details on the various formats. Why do you care about the different formats? Well, it depends on your system and so forth, but here's an example of this matmult with the same matrix, but stored as AIJ, block AIJ, or because the matrix is symmetric, storing in a symmetric format. So when you store it in the symmetric format, you get almost twice the floating point performance because of the way you can arrange the data. So there's a real benefit in that case of using this format as opposed to that format. Similarly over here, switching from AIJ to the block version, well, let's look at this guy for the solves. From the non-block version to the block version, you get almost twice as much performance. And the switches between these is all something you do at runtime. You don't have to rewrite your code. Okay, this is the same kind of construction as we did for vectors before, so I won't go into details about it. There's one part that's interesting for the future here, so I'll go through this part is, let's say we're looking at a multi-physics problem where you actually have 3 types of unknowns, what are called A, B, and C here. And you're doing a Newton's method, and the Newton's method now needs the Jacobian for the entire thing, but the Jacobian itself is naturally splits into this part. The Jacobian associated just with A, the coupling of A and B, A and C, and so forth. So we can think of this in a variety of ways. We can think of it as just being one old Jacobian, but we can also think of it as being separate pieces of the Jacobian, one for each of the parts. And the user might want to, or might already have code to assemble, let's say, just this part here. Say they already have code to assemble these 3 pieces, and they don't want to rewrite the code to assemble the whole thing directly. So we have something called mat-get local submatrix, which is a trick to allow the user to use that old code and think about having 3 different independent pieces that generate different pieces of the Jacobian that don't know about the entire matrix. So what mat-get local matrix does is it returns a new matrix that's a view into the old matrix. So what it means is it's not going to store the matrix, but it's a way of putting values into the larger matrix only with reference to your smaller matrix. So each of the independent pieces of the code then don't have to know that they're being embedded in a large matrix. They get back this matrix where they put values into it, and behind the scenes, PETSc is actually putting the values into the larger matrix for them automatically. This is an interesting slide. It tries to show the many, many choices that you have in PETSc. So here, this is just a subset of the ODE solvers we have. This is a subset of the nonlinear solvers, a subset of the Krylov methods, subset of the preconditioners, a subset of the different matrix types, and so forth. Depending on your problem and how you want to solve it, you make various choices all along the way in selecting the pieces. How does one manage then making all these choices? The way we've organized things in PETSc is we don't want you to have to recompile your code every time you change your choices as to solvers that you want to use. So we have something called the options database, as I mentioned before, and every object in PETSc has a set from options method. So our nonlinear solvers are called SNES, and they have a SNES set from options. If you call that on a nonlinear solver object, it looks in the options database, finds anything related to that object, and uses those choices. So, for example, if you put in on the command line SNES type Newton TR, then when you call SNES set from options on an object, it'll find that and it'll change the solver type to a trust region Newton method. If you put into the command line SNES RTOL, it'll load the tolerance into that SNES object, the tolerance that you've chosen. If you want to look at an object that is get an ASCII representation of what it's actually solving, then you can put a SNES view on the command line, and the SNES set from options will cause the SNES object to be displayed. Similarly, if you want to watch the convergence of the Newton method, or whatever nonlinear solver you're using, if you put a SNES monitor on the command line, the SNES set from options will look for that, and it'll turn on monitoring of it, that is display of the solution process. Similarly for linear solvers. This is true not just for SNES, but for the TS, for the linear solvers, the Krylov methods, the preconditioners, and so forth. So here's an example of using the options. In this case, we're running this nonlinear solver problem, and we're turning on monitoring of the nonlinear convergence. We're refining the mesh twice before we solve the problem, and we're setting the initial size of the mesh there. Here we're, again, turning on the monitoring. We're choosing a preconditioner type of LU So we're saying use a direct solver as our linear solver without having to change the code at all.
So like, if I were to use like this is kind of a little bit back towards the matrices, but if I were to use a DMDA or DMplex, like every process will have both the local and the ghosted portions. And so like in the solver, is the solver going to only look at the local portions of each matrix and vector?
Now, what the DMs do is they give you, they store information about what's needed in terms of communication for the ghosts and the local. And they give you a way of creating vectors that can contain either a global version or a ghosted version. So you, as the programmer, can choose to create as many of these vectors of the two different types that you need and work with them. Internally in the solvers, they work always with the global representation. Because for the linear algebra, there's no inherent advantage in having this local representation. So as Newton method runs, as the preconditioners run, those are always only working with global vectors. It's only when it comes to you're providing a callback function like iFunction or right-hand side function or SNES set function, that's the point where you want to access ghosted local vectors in order to be able to do your calculation.
So like so for instance the DA, if I had a stencil width of 1
Yep.
versus a stencil width of 2, and if they form the same matrix, in terms of the solver performance, is it going to be roughly the same?
Well, the matrix with the stencil width of 2 will have a lot more non-zeros in it. So naturally, it'll take longer to run, likely. Of course, you're going to have higher accuracy because you're hopefully using a higher order method, so you might win. But you change that stencil width, it definitely will change the non-zero structure of the matrix a large amount. So here, what's happened when we have the monitor flag on, it shows the convergence of the 2 norm of the function evaluation. There's a variety of other choices here. Here's what you get when you do a SNES view. So people often ask us, well, what is the solver actually doing? What algorithm is it using? You can always answer that question by running with the appropriate command line option of SNES view or KSP view. And what it does is it prints out in detail exactly what algorithm is being used at that time. So in this case, its type is LS, which stands for line search. And then it tells us details of the line search. It's using a cubic line search and various parameters in the line search. Then it's telling us the maximum function evaluations allowed, the maximum iterations allowed, and so forth for the nonlinear solver. And then below that, it's providing information about the linear solver. It's using GMRes and details about the GMRes method, and so on. And then it's using left preconditioner, and then below that, it shows information about the preconditioner. So the rest of the time is a little less emphasis on PETSc, but it's very important if you're serious about high-performance computing, is once you have a code and it's kind of running, and you say, OK, I want to optimize this. Well, what does that really mean? You can't just randomly take some code and, quote, optimize it. You have to know a bit about the algorithms that's being used. And very important, you have to understand what you're trying to optimize for. Trying to optimize for memory usage, for time. So there's a couple of definitions here, which you should be familiar with already. Strong scalability and weak. Depending on what your problem you're solving, you may be optimizing for one or the other. Both are completely reasonable things to want to optimize for, depending on your situation. So there's this great quote from Bill Grupp: the easiest way to make software scalable is to make it sequentially inefficient. We don't want to do that. What we want to do is we want to have code that's sequentially efficient and also scales really well. We want efficient software. So fundamental to that is you need a performance model for the calculation that you're doing. What this means is an understanding of how the memory bandwidth and latency, the flop rate of the machine, like the floating point units, reduction operations that occur across the machine. you have to have a model for all of these things. And what that model means is a simple formula, little algebraic formulas that tell you what you expect to get based on the memory bandwidth of the machine, the latency of the machine, how fast the floating point unit can issue instructions, and so forth. And in addition to that, you need to have some profiling information so you can match what your program is doing to the model. And if you see that the model predicts something your program is not doing, then you have to either realize your model is wrong and adjust your model, or go into the code and understand why it's not matching your model. But this is really important. Without a model, performance measurements by themselves are not really that useful. So you run the code, it takes an hour, and you say, oh, 80% of the time is in the linear solver. If you don't have a model of where the time should be, you don't know if that 80% is good or bad. It may be that inherent it should be 80% of the time. So you shouldn't go and optimize the linear solver because you'd be wasting your time. You have to have this model in order to be able to interpret the logging information that you get out. Now, this is a very grand slide here, which I think Jed probably contributed. But ideally, you have a model of the computation, the memory usage, the communication, the bandwidth you're going to need, how much concurrency is already there. Getting all of this, of course, is quite complicated. So it's fine to start with really simple models where you only consider a couple of things and then start building up with those over time. So here's a couple of formulas that are useful for understanding the performance that you can possibly get for floating point performance based on the memory bandwidth of your system. And from that, the stream benchmark is this really useful tool to tell you what kind of memory bandwidth you can actually get out of your system. And almost always for PETSc programs, the stream benchmark is the starting point for understanding what kind of performance you can get. If your code is giving you the type of memory bandwidth usage that stream gives you, you're pretty much done at that point. Your code can't be improved very much. Your algorithms possibly could be replaced with completely far better algorithms, for example, all the work that Jim Demmel does, but the code is pretty much implementing the algorithm as best it can be. So here we go into details of an explicit, simple, sparse matrix vector product and build up a simple model of performance. This is what the next few slides are. And how this is done, we're not going to understand the details, of course, there's no time for that. But how this is done is to look at the loop structure, look at the operations that are done in the loop structure. So in compressed sparse row matrix storage, you loop over the rows, you loop over the non-zero columns, you accumulate this sparse vector-vector product. Now, for each of these, you can look at how many operations you're doing, how many loads you're needing to do, like on A, how many indirect loads you need to do, like on X, where you're doing an indirect load with this piece. So you can calculate, count up, and get a little formula for these things. And then you can make some assumptions about the caches and so forth to simplify your model. And then you can end up with formulas. So an example down here is the potential upper bound that you can get based on a given bandwidth. Now in this case, what it's done is V is the number of vectors that we're multiplying at the same time. So under normal circumstances, I believe V would then be, number of vectors to multiply. Normal circumstances, V would be 1. So we end up with this formula, which tells us the expected floating point rate that we're going to get based on the bandwidth. And then you can actually run the code, and you can see what the bandwidth is and compare. See what the floating point rate is and compare, and verify whether your code is giving you what you need or not. And obviously, larger number of vectors, the better the performance you get. But we don't have time for all those details. Many more details on this piece. How to get the profiling information from PETSc. Again, you can look at it afterwards, and then you can talk to me. I'll be here all day.